Section: Introduction. In this section, we discuss the significant advancements in language model agents, which have shown the ability to autonomously handle complex real-world tasks. These agents utilize language models to suggest actions that can be executed through API calls in various settings, leading to applications in software engineering, robot control, and scientific research. Typically, these agents interact with their environment to collect information, reason about it, and then take actions to meet specific goals. However, effectively exploring the environment remains a challenge. Recent studies have tackled this issue by creating agentic frameworks with well-designed tools and external memory systems for better information gathering. While these methods have shown promise, they often depend on human-designed frameworks tailored to specific tasks or models. This reliance arises from the common belief that agents work with limited visibility, requiring them to actively gather observations to understand their environment. While this is true in some scenarios, like a visual language model controlling a robot in an unfamiliar space, many tasks, such as those in SWE-bench, provide full access to the environment from the start. We question whether tasks like those in SWE-bench can be approached with simpler architectures. Specifically, we explore what we might sacrifice if we replaced complex information gathering processes with a single long-context language model. This inquiry is crucial for understanding agent design. Although a pure long-context language model approach may be more costly than an agentic system, if it proves competitive with complex methods, advancements in long-context models could lead to simpler, more unified systems that are easier to train. Our research begins to address this question by examining SWE-bench, where existing methods use complex agent frameworks without needing active information gathering. We propose a straightforward approach that utilizes long-context language models to solve problems with complete information about the environment, simplifying agent design to a prompting task. Through our testing with SWE-bench verified, we identify effective prompting techniques that enhance performance, showing that our method outperforms scaffolding-based approaches using the same language model. However, we still observe a performance gap compared to state-of-the-art agent systems, mainly due to the weaker coding abilities of long-context models. To bridge this gap, we demonstrate that a hybrid approach, combining the long-context capabilities of these models with the problem-solving strengths of short-context models, significantly improves performance. Our contributions include showing that long-context models can simplify agent design in software engineering tasks, outperforming more complex systems by 3 to 6% without any scaffolding. We also identify simple prompting techniques that improve performance significantly. Our framework achieves competitive results, with specific models reaching solve rates of around 48.6% to 50.8% using our methods. In the related work section, we note the growing interest in developing language model agents for software engineering tasks, particularly on benchmarks like SWE-bench. Recent strategies can be divided into agentic frameworks, which treat language models as autonomous agents, and non-agentic pipelines that focus on specialized execution processes. Our work stands out by leveraging long-context models to directly process the entire environment state, achieving results comparable to more complex, engineered methods. Additionally, advancements in long-context models have shown that they can outperform retrieval-augmented systems, even without specific training, indicating their potential to replace traditional memory and information-gathering processes in language model agent scenarios. Section Summary. In this section, we explore the potential of long-context language models, LCLMs, to simplify agent design for software engineering tasks by directly processing complete environment state information, rather than relying on complex scaffolding methods. Our findings indicate that LCLMs can outperform traditional agentic systems in certain scenarios, and we propose a hybrid approach that combines the strengths of both LCLMs and short context models to further enhance performance. Section: Method. In this section, we discuss our method for designing language model agents. Traditional methods assume that the environment is too vast to observe directly, leading us to rely on interactive exploration to gather information. This makes sense for humans and in online environments, But many applications, like multi-hop question answering and software engineering, do not need active information gathering. Instead, a long context model could potentially provide answers directly when given the entire environment. We illustrate this contrast in our figures, showing two approaches. One that uses tools and execution loops for information gathering and another that encodes the context as a long prompt. For complex tasks like bug fixing, the entire state of a repository is often compact enough to fit within the context limits of advanced models, like Gemini, which can handle 2 million tokens. This leads us to ask if we can include the entire state in the agent's context, allowing for full observability and reducing the need for iterative exploration. We propose state-in-context agents that utilize powerful long-context language models, LCLMs, capable of processing millions of tokens. This approach simplifies the design by removing the need for complex scaffolding, turning open-ended tasks into closed-ended ones where LMs perform well. We first present this concept and then detail our implementation. In our standard agent formulation, we typically work in partially observable settings. An agent is created to solve a task, like fixing a bug, within an environment defined by its state, which includes all files and their relationships. The agent explores this environment by taking actions to gather observations, which ideally reconstruct the necessary information to complete the task. Existing frameworks often require specialized tools for exploration, but we leverage LCLMs to create a state-in-context agent that receives either the full state or a compressed version that retains relevant information. This allows the agent to explore in context, using its understanding to extract necessary details and produce solutions directly. By including the entire environment state in the model context, we trade off some precision for better recall of relevant information. We also develop state-in-context agents specifically for software engineering tasks using SWE-bench, which is a suitable testbed for our ideas. Our goal is to create a simple workflow that minimizes manual curation while maximizing the utility of LCLMs. The core of our workflow involves using LCLMs to process the entire code repository and directly output solutions, similar to zero-shot prompting tasks. When repositories are too large for the context window, we implement a state compression step based on the directory structure to filter out irrelevant files. We anticipate that as LCLMs improve, this issue will diminish. Our compression method ranks files based on relevance to the issue, allowing us to include as many relevant files as possible within the context limit. For repositories that fit within the context, our DIRECTSOLVE method prompts an LCLM to generate solutions based on the problem statement and the entire repository state. We enhance performance with two prompting techniques: code restatement, which helps retrieve relevant code, and chain of thought prompting, which breaks down the solution process into smaller steps. To address the limitations of LCLMs, we propose a two-stage SELECTSOLVE method that combines the strengths of LCLMs and specialized short context language models, SCLMs. In the first stage, an LCLM identifies and compresses the state, which is then passed to an SCLM for problem solving. This method allows us to leverage the advantages of both types of models while keeping the process simple. Both our methods generate patches using a specific format that clearly defines the original code and its replacements, enhancing precision and reducing errors. For validation, we use a methodology that includes generating tests to verify fixes and applying regression tests to ensure functionality remains intact. Our framework can easily scale by generating more samples or multiple patches, accommodating computational needs effectively. Section Summary. In this section, we propose a novel approach for designing state and context agents using long context language models, LCLMs, that can process entire environments, thereby eliminating the need for interactive exploration in tasks like software engineering. By leveraging LCLMs capabilities, we develop methods such as DIRECTSOLVE and SELECTSOLVE to efficiently generate solutions directly from the full or compressed state of code repositories, enhancing performance while minimizing the complexity of agent scaffolding. Section: Experiments. In this section, we describe our experimental setups. We demonstrate the effectiveness of our method in an end-to-end context, showing results comparable to heavily engineered agentic scaffolding. We also present an extensive ablation study that highlights important design choices for creating state-in-context agents using LCLMs. Finally, we evaluate the robustness of our approaches across various LCLMs. For our benchmark, we use the SWE-bench verified dataset, which includes 500 carefully selected software engineering problems validated by experts. This dataset is a subset of the original SWE-bench and maintains its structure of real-world GitHub issues and pull requests from 12 open-source Python repositories, with correctness confirmed through unit tests. In terms of implementation, we utilized GEMINI 1.5 Pro with a context of 2 million tokens and GEMINI 2.5 Pro with 1 million tokens as our LCLMs. For SELECTSOLVE, we also assessed CLAUDE 3.7 Sonnet, which shows top performance on coding tasks. We selected the top 6 files for SELECTSOLVE, meaning our repair model used content from these 6 files to generate patches. Following previous work, we set a temperature of 0.8 for sampling different patches and selecting the best one. We generated 8 patches for each instance and selected one based on majority voting. We compared our method against 2 main categories of previous approaches: agentic frameworks and non-agentic scaffolding. While some prior works focus on scaling up inference time compute, our goal is to showcase our scaffolding-free agent approach as a competitive alternative. We chose Agentless and Code Act as our baselines, representing the best in their respective categories. We primarily used GEMINI 1.5 Pro, GEMINI 2.5 Pro with the Google search tool disabled, and CLAUDE 3.7 Sonnet for comparability, including GPT-4o for reference. Agentless was specifically designed for GPT-4o and CLAUDE 3.5 Sonnet, but it did not transfer well to Gemini models due to parsing errors. We adjusted the pipeline to ensure correct parsing and reported both pre- and post-curation results. We also evaluated intermediate caches of GPT-4o trajectories for accuracy. In all agentless configurations, we sampled 4 instances of relevant code and generated 2 samples from each to create the 8 patches for selection. Code Act is an open-source framework that implements an interactive language model-based agent. We used a specific commit with a maximum iteration limit of 60, where each iteration involves generating observations and actions. We restricted the toolset to basic functionalities, disabling web browsing to maintain benchmark integrity. For evaluation metrics, we reported the pass at 1 rate, which measures the success rate of the final selected patch for each method. For our method and the agentless approach, we also reported the pass at 8 rate, indicating the likelihood of at least one patch solving the issue among the 8 samples. In our end-to-end results on the SWE-bench verified dataset, we found that our DIRECTSOLVE method with LCLMs outperformed agent scaffolding. Specifically, when using GEMINI 1.5 Pro, our DIRECTSOLVE method surpassed the best baseline, agentless, by 6% in pass at 1, with statistical significance. Using GEMINI 2.5 Pro, we achieved a 6.2% improvement in pass at 8 metrics. Our DIRECTSOLVE method effectively prompts an LCLM to reason and solve problems based on the entire environment state, demonstrating that LCLMs can function as scaffolding-free agents. Interestingly, our DIRECTSOLVE method performed similarly to our SELECTSOLVE method with the same model, showing only a 1.2% lower pass at 1 rate. This suggests that minimizing agentic workflows could be beneficial as LCLM capabilities improve. When we used CLAUDE 3.7 Sonnet for SELECTSOLVE, performance increased significantly from 39.2% to 48.6%, showcasing the potential of leveraging advanced problem-solving capabilities of SCLMs. While SELECTSOLVE outperformed agentless, it did not match OpenHand's Code Act, indicating that specialized tool design may still provide additional benefits. We also observed that scaffolding-based approaches do not transfer well across models. These methods often rely on specialized tools and workflows tailored to specific models, which may not work effectively with others. We found that direct transfer to GEMINI 1.5 Pro resulted in a significant performance drop for both baselines, with agentless dropping to 11% and Code Act to 18.8%. This highlights the limited robustness of standard scaffolding-based approaches and the need for human effort in model-specific adaptations. Therefore, our simplified framework requiring minimal curation may be more advantageous. Section Summary. In this section, we describe our experimental setups and demonstrate that our method, DIRECTSOLVE, outperforms traditional agentic scaffolding approaches in software engineering tasks, achieving significant improvements in pass rates with minimal engineering effort. We also highlight the limitations of scaffolding-based methods in transferring across models, emphasizing the advantages of our simplified, adaptable framework. Section: Ablation Study. In this section, we systematically analyze different components of our methods to understand their contributions to overall performance and identify key factors that allow LCLMs to work effectively without scaffolding. In our ablation study experiments, we measured performance without additional patch validation to focus on the intrinsic patch generation abilities of LCLMs across various setups. To determine which design choices are important, we examine different aspects of our DIRECTSOLVE method. We present our findings in a table and discuss them below. First, we looked at the prompting techniques we used, including chain-of-thought prompting, relevant code restatement, and adding file index information. Our analysis shows that chain-of-thought prompting is essential for agent performance. Removing it results in a significant drop in performance, specifically a 23% decrease in the first pass success rate and a 34% decrease in the eighth pass success rate. This highlights the importance of reasoning in bug-fixing tasks. We also found that relevant code restatement positively affects the first pass success rate but does not significantly impact the eighth pass success rate, which measures solution coverage. This suggests that while it may not enhance maximum problem-solving ability, it does improve the stability and consistency of our method. Additionally, we discovered that adding file index information, although it seems minor, is important. Next, we analyzed the impact of removing comments and doc strings from the repository to shorten the context length. This change reduced the average token count from about 2 million to 1.4 million and improved performance by 5% in the first pass success rate and 6% in the eighth pass success rate. This significant improvement indicates potential inefficiencies in current LCLMs when handling very long contexts. We then explored how LCLMs enhance localization in our SELECTSOLVE method. The agentless framework uses a localization scaffolding that combines direct prompting with embedding-based retrieval, while our SELECTSOLVE method prompts the LCLM directly based on the compressed repository. We compared the localization performance of these two approaches by measuring file-level localization errors. Our results show that using a single LCLM directly can reduce file-level localization errors by over 15% compared to the scaffolding method. Furthermore, when we aggregated results from 8 samples using majority voting, the localization error decreased by about 25% to 35%. This demonstrates that LCLMs not only simplify the localization process but also significantly improve accuracy. We also examined how the location of the target file affects agent performance. We found that the long context processing capabilities of LCLMs might limit their ability to absorb information, leading to issues like getting lost in the middle. To investigate this, we varied the placement of target files within the context and measured the performance of direct solve. Our findings indicate that the position of target files significantly affects performance, with the best results occurring when target files are placed at the front of the prompt. This supports our design choice to order files based on their relevance during the state compression step. To ensure our prompts and results are not overfitted to a single LCLM, we tested different models with context windows of at least 1 million tokens. We randomly sampled 100 instances for this evaluation and did not apply patch validation to measure the pure patch generation abilities of different models. The results showed that GEMINI 2.5 Pro consistently performed the best across all metrics, achieving a 51% solve rate on a random subset of 100 instances without any patch selection. Notably, DIRECTSOLVE outperformed SELECTSOLVE methods in the GEMINI 2.5 Pro experiments, suggesting that as LCLMs improve, the performance gap between minimal prompting frameworks and scaffolding approaches may narrow or even reverse. All methods achieved a solve rate of over 20%, indicating that our experimental setup and prompts are not overfitted to a single LCLM. Minimax Text 001, the only open-weight model we evaluated, did not match the performance of the closed-source models but still resolved 20% of instances using our SELECTSOLVE method. Section Summary. In this section, we systematically analyze the contributions of various components in our methods, revealing that chain-of-thought prompting is essential for performance, while repository compression improves efficiency. Our findings also indicate that the positioning of target files significantly affects performance, and as LCLMs evolve, the gap between minimal prompting and scaffolding approaches may diminish. Section Discussion. In this section, we discuss the cost analysis of our methods compared to agentless and code-act. The average costs for these methods are 0.25, 0.87, and 2.6, respectively, showing that using LCLM is currently less cost-effective. However, we note that the costs for language model inference have dramatically decreased, with GPT-4 API costs dropping by a factor of 1,000 over the past 3 years. Additionally, the context length for capable models has increased significantly, from 4,000 tokens for GPT-4 to 2 million tokens for GEMINI 1.5 Pro. Our findings indicate that LCLM-based agents possess the necessary capabilities to be effective, and optimizing inference can lead to simpler agent designs. In practical scenarios, users often query the same codebase multiple times, which can lower average inference costs through key-value caching of codebase tokens. After implementing this caching, the remaining inference cost primarily comes from the context caching token cost of the long codebase, which is about 1/4 of the total cost per instance. As a result, after the first inference on a codebase, the cost drops to around 0.725 from 2.6. While KV caching makes inference costs competitive with existing agents, we recognize that many codebases in the SWE-bench verified datasets have slight variations due to different commits, indicating that further work is needed to maximize these cost savings in real-world software engineering agent scenarios. Beyond SWE-bench, our approach may also influence methods for gathering information from the environment and learning from past interactions. With code-act trajectories averaging 77,700 tokens and generative agent simulations reaching about 50,000 tokens, these long trajectories fit well within the context windows of modern LCLMs. This suggests that LCLMs could simplify complex memory and retrieval systems for interactions with language model agents.